Hello everybody, my name is Enrique Moliner and I work at the Department of Sustainability and Industrial Recovery of AIMPLAS. AIMPLAS is a technological center with more than 25 years of experience providing support to companies belonging to the plastic industry, including manufacturers and suppliers of raw materials, plastic converters, end users, and also plastics recyclers. We provide support to these companies through the coordination and execution of research and development projects. We also provide service for analysis and testing. We also provide technical advice, competitive intelligence services, and specialized training. At my department, at the Department of Sustainability and Industrial Recovery, we work on promoting the sustainability of the plastic sector through the implementation of eco-design, through the improvement of the environmental performance of the plastic products. We also work on the development and application of bioplastics, both bio-based plastics and biodegradable plastics. And finally, we also work on plastics recycling. In fact, what I'm going to present you today is the use of recycled plastics in food packaging. The contents of my presentation are the following. First, I will start with an introduction of the needs and benefits of using recycled plastics. We will continue by reviewing the current situation of recycled plastics in contact with food. We will show the different possibilities we have to use recycled plastics in food contact applications, and we will then analyze in more detail one of these possibilities, which is the use of recycled plastics behind a functional barrier. And we will also show some of the developments conducted by AIMPLAS in this field, in the field of functional barriers, through our participation as project coordinator of the European project VANUS. And finally, I will highlight some relevant conclusions. So I'm going to start with the introduction. Here you have this graph which shows the European plastics demand by polymer type and market sector. And what we can find is that packaging sector is the sector with the higher plastics demand, with about 40% of the consumption of plastic materials. And the success of plastic materials in this sector, in the packaging sector, is mainly due to their excellent versatility as a result of the combination of their diverse properties like transparency, lightness, good mechanical properties, stability against environmental conditions, and so forth. However, one of the most controversial issues of plastic materials in general and plastic packaging in particular is the end of life, because this kind of products become waste when they reach the end of their useful lives, and this waste is not always managed in the best way possible. Here you have the rates for treatment for post-consumer plastics waste in Europe for the year 2014, and you can see that this year about 26 million tons of post-consumer plastic waste were generated, and of this amount about 31% still went to landfill, while the recycling of this waste was limited to about 30%. The remaining amount was sent to energy recovery. So we still need to invest extra efforts on boosting the recycling of plastics. The recycling of plastics is necessary for several reasons: for legal reasons, for environmental reasons, and also for economic reasons. The new European policies, the new circular economy model that is being implemented in the European Union requires that all waste is processed and converted again into resources to avoid or to reach a very very optimistic objective of zero waste to landfill. In this way, plastic waste must be considered a valuable resource, and it should be recycled to be reintroduced in the production system. And only those waste that cannot be recycled anymore should be recovered through incineration with energy recovery. But we should be able to prioritize recycling over energy recovery, because recycling, according to the waste management hierarchy, is a preferable option from the environmental point of view. In this figure, we can see the environmental benefits of recycling. Here we have the carbon footprint of recycled materials compared with the carbon footprint of their equivalent virgin materials. And what we can find is that for most materials, the difference in carbon intensity, because of the difference in energy intensity between virgin and recycled sources, can be enormous. In fact, recycled materials and recycled plastics are much more less energy intensive than their equivalent virgin plastics, and therefore the carbon footprint is lower. But companies can also benefit from the use of recycled plastics in economic terms, because, as you know, recycled plastics usually have a lower market price than their equivalent virgin plastics. Here we have a comparison of the market prices between virgin plastics and recycled plastics, and we can see that the price of recycled plastics is between 30 and 60% cheaper than their equivalent primary raw materials, depending on the type of plastic and on the type of recyclate. You know that plastic regrinds are cheaper than recycled plastics in regranulates or in a pellet form, in a pellet shape. But how we can boost recycling? Well, in AIM+, we work in the boosting of recycling by addressing two main lines of activity. The first one is the improvement of the recycling process to improve the quality of the resulting recycled materials. For instance, through the decontamination of critical substances, the removal of critical substances, the removal of odors in plastic packaging, ways to close the loop of these materials. And we also work on the identification and development of new applications for recycled plastic materials, for instance, in the manufacturing of food packaging with recycled plastics. In fact, this is the topic we are presenting hereinafter. But first of all, we are reviewing the current situation of recycled plastics in contact with food. There is a framework regulation on food contact materials and recycled plastics in food contact materials, and this framework regulation is mainly focused on ensure the food safety. Framework regulation is defined in the European Union by the European Commission based on the findings of the EFSA, the European Food Safety Authority, which is the agency of the European Commission to provide independent scientific advice and support on food safety issues and on issues related to food contact materials. While in the USA, this role is performed by the FDA, but by the Food and Drug Administration, and the legal framework in the European Union and the legal framework in the USA are very similar or are roughly the same. Here we have an overview of the European Union legal framework on food contact materials. First of all, we have a framework regulation, the Regulation 1935, which provides the general basis for all food contact materials. Their objective is to ensure the food safety, to ensure the protection of human health, and to this end it provides requirements for key aspects like the labeling of the food contact materials, the requirements for the declaration of compliance that must be provided by suppliers or manufacturers of food contact materials, and it also provides requirements for traceability to ensure this food safety of the materials. This framework regulation is also supported by another regulation, by the Regulation 2023, which provides rules for good manufacturing practices for food contact materials. What this regulation provides is the requirements for the quality assurance and control systems that allow the companies to ensure and to demonstrate the compliance with the requirements of the framework regulation on food contact materials. And this framework regulation, the Regulation 1935, also mandates the establishment of specific requirements for specific food contact materials like ceramics or plastics or even recycled plastics. And some of these requirements have already been implemented through specific regulation, like the regulation of the European Union 10 of the year 2011 for plastic materials, and also the specific regulation for recycled plastic materials, which is the Regulation 282 of the year 2008. Regulation of the European Union 10 of the year 2011 address the requirements for plastic materials for food contact applications, and what this regulation provides, first of all, is a positive list of the substances that can be used for the manufacturing of plastic materials for food contact applications, including monomers, but also their additives. And this regulation also provides the requirements for the migration testing, both for the methods to be followed for the overall and specific migration testing, but also the limits that must be applied to food contact materials to be able to ensure this food safety. According to this legal framework, we have three different possibilities to use recycled plastic materials for food contact applications. The first possibility is the use of cuts or scraps from the production of plastics for food contact applications. This waste can be directly used or directly reintroduced into the same production process for produce, again, food contact materials or food contact products made of plastics. But it should be mentioned that this kind of waste is a very valuable waste because it has a very well-known composition, it is very homogeneous, it is a controlled waste, so companies usually reintroduce this waste into their processes, so there is a very low availability of this kind of waste in the market for secondary raw materials. Hence, if we want to use recycled plastics, we probably have to do it through some of the other two possibilities we are presenting now. The second possibility is the use of recycled plastics from processes authorized by the EFSA. In this case, we can use post-consumer plastic waste, so the availability of this waste is either done in the case of cuts and scraps, which is pre-consumer waste or post-industrial waste. So there is a neither availability, but in this case the recycled plastics must come from waste from food contact applications. We can use post-consumer waste, but it must come from food contact applications. In this case, the European Food Safety Authority is responsible for the risk assessment of the recycled processes in order to demonstrate that these processes are able to decontaminate the plastics in order to guarantee the food safety of the recycled plastics in food contact applications. There are several positive opinions from the EFSA for several recycling processes, but the final decision of granting or refusing the recycling process must be done by the European Commission, and there is a delay on the granting of these processes, but at the moment, for instance, in Spain, there is a provisional situation in which it can be used recycled plastics coming from processes which have obtained a positive opinion by the EFSA. But the limitation in this case is done by the fact that the plastic that can be used for these applications must come from food contact, from a food contact origin. While the third possibility we have is the use of recycled plastics behind a functional barrier. In this case, we can also use post-consumer plastic waste, but the advantage is that the waste is not, do not necessarily come from food contact origin. And we are now focusing in this third possibility of the use of recycled plastics behind functional barriers. A functional barrier is a layer or a multi-layer within food contact materials on all articles, which is able to prevent the transfer or the migration of substances from behind that barrier into the foodstuff. In this figure, we have a bilayer system with a functional barrier of virgin plastic, which is in direct contact with the foodstuff, and behind that functional barrier we have recycled plastic. The function of this barrier is to prevent the transfer of pollutant substances or non-authorized substances from the recycled layer to the food. Note that we can also use a symmetrical structure, a symmetrical multi-layer structure with the two functional barriers in the outer layers and a recycled layer in the inner layer. In this case, the symmetrical structure could be used to also prevent the set-off effects in the case of stockable packaging. For instance, we can prevent the migration from the recycled layer in films, or we can also prevent the migration of the recycled layer not only to the foodstuff but also to the inner layer of teacups, for instance, when they are stored in stockable packaging. Okay. Behind a functional barrier, it is possible to use non-authorized substances, provided that they fulfill certain criteria and provided that the functional barrier is able to prevent the migration or to allow that migration remains below a given detection limit. In this case, the detection limit is 10 parts per billion. But it should also be noted that not all substances are covered by the functional barrier concept. There are some substances like mutagenic substances, carcinogenic substances, or substances toxic to reproduction or nanoparticles that cannot be used under this concept of functional barrier. Moreover, the effectiveness of the functional barrier depends on several parameters, depends on the recycled layer, on the concentration of contaminants and the type of contaminants present in this layer. It also depends on the properties of the barrier layer itself, like the chemical nature and thickness of this layer, and there is also very important to define the conditions of use. The migration can also depend on the type of food that is contained in the packaging and also on the temperature and time of use. So the effectiveness of the functional barrier must be demonstrated on a case-by-case basis. There are some well-known functional barriers. We can distinguish between absolute barriers and partial barriers. Absolute barriers can be, for instance, glass or even some metals which are able to ensure a complete blockage for migration, while the partial barriers like plastics may reduce the migration of substances below specific migration limits or detection limits. Here we have some examples of of polyethylene terephthalate as functional barrier. Polyethylene terephthalate is the polymer most studied as functional barrier. And in this case, some studies performed by the FDA, by the Food and Drug Agency of the USA, have demonstrated that polyethylene virgin can be used as functional barrier for recycled polyethylene at room temperature if the thickness of the virgin PET is over 25 microns. While for higher temperatures, it can also be used as functional barrier for recycled PET, but in this case the thickness must be over 50 microns. But as I said before, if there is not scientific evidences on the effectiveness of the functional barrier, we will demonstrate this effectiveness of the functional barrier case by case because of the different parameters that could affect this effectiveness. The method that we use in A+ for demonstrate the effectiveness of a virgin polymer with a given thickness as functional barrier for other polymers or even for other materials is the following. First of all, what we do is to contaminate the virgin polymer with a known concentration of surrogate substances, what it is known as a challenge test, and we use this polymer to simulate a recycled plastic in the worst scenario possible, with the highest concentration of pollutants. Then we use this contaminated polymer and incorporate it into the inner layer of the finished article of a multi-layer structure using virgin polymer as the functional barrier layer. And finally, what we do is to perform migration tests with food contact simulating solvents under the worst foreseeable conditions of use, and we determine the migration that is produced through the simulants. And in these ways, we are able to check if the virgin polymer with the given thickness is able to prevent migration or not, is able to act as a functional barrier or not under these worst conditions. Here we have some examples of functional barriers. These are results from a study on functional barriers performed by the Young Research Center of the European Commission. And we have different polymers that can be act as functional barriers under different contact conditions and with different molecular mass range of migrant of the layer used of recycled layer. We have examples for low density polyethylene, for polypropylene, for high density polyethylene acting as functional barrier, also for PET, and also for other materials typically used for food packaging applications like polystyrene or even polyamides. And we also have some examples of functional barrier films, in this case at contact conditions of 10 days at 60 Celsius degrees. And what we can see here is that not only polymers can be used as functional layers, but also different types of coatings could perform this functional barrier also. Well, I'm now going to present you some of the developments A+ has done in this field as the project coordinator of a European project, the VANUS project, which consisted on the definition and development of functional barriers for the use of different types of recycled materials in multi-layer food packaging. This is a European project funded by the European Commission under the 7th Framework Programme. And what we did here was to develop functional barriers for different types of packagings for 3 different case studies. The first one was the development of a semi-rigid multi-layer plastic packaging, which was initially made of polypropylene and ethyl vinyl alcohol for improved barrier properties. It was processed by co-extrusion, and we, in Vanus, what we did was to use polypropylene as functional barrier for recycled polypropylene in this tray for food contact applications. The second development was a flexible multi-layer multi-material packaging, and in this case we use the polyethylene and metallized PET as barrier for recycled paper. In this kind of packaging you can see in the slide. And the third case study was the use of a coating as a functional barrier for recycled paperboard. Well, and finally I would like to highlight some conclusions. We have seen that there are 3 different options to use recycled plastics in food contact applications. We can use pre-consumer waste or post-industrial waste. We can directly use of cuts or scraps from the production of plastics for food contact applications, of plastic products for food contact applications. We can also use recycled plastics, post-consumer recycled plastics coming from processes, for recycling processes authorized by the EFSA. And the third possibility is the use of recycled plastics behind a functional barrier. We can, in this case, use post-consumer plastic waste, and this waste have not necessarily come from food contact origin. I have also said that the effectiveness of the functional barrier must be demonstrated case by case, because there are different parameters that can affect this effectiveness of the functional barrier. And I would also like to highlight some of the findings of the Vanus project. What we have found in this project was that some diffusion effects might appear during certain processes. In this case, during co-extrusion, there are moments where the functional barrier and the recycled layer are in a melting state, and in this case we can have some migration, some diffusion effects from the recycled layer to the functional barrier, and in this case we must be able to analyze and minimize these effects to be able to ensure the food safety of the packaging. Also note that these kind of effects won't appear in lamination or in injection processes. And finally, I would like to also highlight that the conditions of use related to the functional barrier must be clearly established in the declaration of compliance. We must specify the type of functional barrier, the materials, and the temperature of use, and the type of foodstuff for which the functional barrier have been developed to be able to ensure the food safety of the packaging or of the food contact article. And that's all. Thank you for your attention, and if you have any question or any doubt, please do not hesitate to contact me through my email or through the phone number. Thank you very much again, and see you.